Section 4.5 is looking at derivatives in the shape of a graph. What we're really concerned with in this section is looking at a function and its first derivative and second derivative and how they all interact with one another. Graphs are a useful medium to do that in, so our problems are going to look like graphing problems, but really what we want to do is understand derivatives better. So we're going to pick up from where we left off in the last section, Corollary 3 from section 4.4 on the intermediate value theorem. So in this corollary, what we did is we looked at a continuous function over a closed interval, and we said if the derivative is positive, then the function is increasing, and if the derivative is negative, then the function is decreasing. And that's something that we looked at earlier in the chapter when we were talking about derivatives. But this gives us a way to look at the direction a function is pointing by just looking at its derivative. We can also think about f prime as being the function that we apply this to. So when f prime's derivative, which is f double prime, is positive, then f prime is increasing. When f prime's derivative, which is f double prime, is negative, then f prime is decreasing. When I look at the derivative increasing, I want to think about a function where the tangent lines are getting steeper and steeper. Okay, so I can think about a graph where if I were to have looked at the tangent lines, here I have a slope that's negative, a slope that's 0, and a slope that's positive, and a slope that's more positive. So the tangent lines have slopes that are getting bigger and bigger or increasing, and I get this shape. We call this concave up. Okay. When the derivative is decreasing, the slopes of the tangent lines will be decreasing. So what that might look like, I'll draw an example graph. We'll draw in some tangent lines here. There's a tangent line that's positive. There's a tangent line that's less positive. A tangent line that's 0. A tangent line a little bit negative. And a tangent line more negative. So as I move from left to right, the slopes of the tangent lines are decreasing. And we call this concave down. So we can break up graphs into a bunch of little pieces. And I can think about, for each of those pieces, what does the shape look like? So I can have my function increasing with two different fundamental shapes. It can be increasing where the tangent lines are also increasing. Okay, so we would call this f is increasing and concave up. Or my function could be increasing with sort of this bent down shape, where the tangent lines are getting less and less steep as we go. So f is increasing and concave down. Likewise, there's two different shapes for a decreasing function. If the function's decreasing and has this bent down shape, that means that those tangent lines are getting more and more negative. So f prime is decreasing, which means that f is concave down. And if f is decreasing but has this bent up shape, that means that the tangent lines are getting bigger and bigger as we go, so f is concave up. Another way that you can think about concave up and down, if I look at these pieces of the graph that are concave up, right? So A and D here are concave up. And if I draw a graph that's concave up, and I look at the tangent lines to that graph, you'll notice that the graph is on top of its tangent lines. And if I draw a graph that has this cup down shape, and I draw in the tangent lines, you'll notice that the graph lies below its tangent lines when the graph is concave down. Let's look at the first derivative test. First of all, it's important to know what this test does for us. The first derivative test is used to tell where a function is increasing or decreasing, and it also tells us where the local maximums and minimums are. So here's the steps to the test. We first find the critical points for the function. Then we draw a number line, labeling the critical points on that number line. This divides the number line up into intervals. So then we pick a number from each of the intervals, and we test that into the derivative f prime. When f prime is positive, that means f is increasing. When f prime is negative, that means that f is decreasing. Then, if we look at the critical points, if the function goes from increasing to decreasing, the critical point is a max. If the function goes from decreasing to increasing, it's a min. And if the function doesn't change, if it goes increasing, increasing, or decreasing, decreasing, then that critical point is neither a max nor a min. So let's look at an example. The first step was to find the critical points for this function. So I'm going to take the derivative. So using the power rule, the 3 comes down, so we get 6x squared minus 6x minus 12 plus 0. And we want to find where the derivative is 0 or undefined. So it's going to be 0 when 6x squared minus 6x minus 12 is equal to 0. I'm going to factor out a 6. Continue to factor. So when x minus 2 is equal to 0, x is 2. When x plus 1 is equal to 0, x is negative 1. So those are 2 critical points. I now check for where f is undefined. It's a polynomial, so that's never going to happen. So I have these 2 critical points, x equals negative 1 and x equals 2. So the next step was to draw a number line and label those critical points. So here I'm going to have a number line, and I only label my critical points. It is not helpful to label things like 0 just because it's in the middle. That can be confusing. So now what we do is we say, I want to look at this as being 3 intervals, and we're going to test a point from each interval. So in this first interval, I'm looking at x values less than negative 1. I'm going to test x equals, say, negative 2 into the derivative f prime of x. Now, we have the derivative written down right here, or you can use the factored form of the derivative. Either one works, right? So f prime is 6x squared minus 6x minus 12, or 6 times x minus 2 times x plus 1. If you're typing it on your calculator, it doesn't matter. If you're just going to use some mental math, then the factored form is typically a lot easier to plug into. So when I plug in, negative 2 minus 2 is negative 4. Negative 2 plus 1 is negative 1. So we get 24, which is positive. What I'm going to label on my number line is that this interval I have tested and the derivative is positive. That means that the function is increasing. So I'm going to draw an arrow that rises up as I move from left to right. Now I'm going to test something between negative 1 and 2. An easy number there would be, say, 0. For 0, I'm just going to plug into this first one because I get 0 minus 0 minus 12, which is negative. Because it's negative, that means that as I move from left to right, the function decreases or moves down. Finally, I pick a number bigger than 2, so I'm going to test x equals, say, 3. When we plug 3 in, we get 6 times 1 times 4, or 24. That's positive. So the function is increasing. A couple of things to note as I do this. I should never have an arrow that points to the left. All you're going to do is confuse yourself. When we talk about increasing and decreasing, what we mean is as x increases, what happens to y? Does it increase or decrease? So as x moves up or moves to the right, what happens to the y values? Do they go up or do they go down? Okay. If you start drawing arrows that point to the left, then you'll be confusing what it means to be increasing and decreasing, and then the visualization will lose its effectiveness. All right, the final step is to say, at negative 1, what happens? And again, the visual here is really helpful. Since the graph is going up and then coming down, I have a max here. At x equals 2, the graph goes down, hits 2, and then comes up. So f has a local minimum at x equals 2. All right, well, this isn't the only way to find a maximum and minimum. We also have something called the second derivative test. The second derivative test does the same thing the first derivative test does. It's looking for local maximums and minimums. Here's how it works. If I have a function that has a critical point and is concave down, remember that that concave down graph had this cup down shape. If I have a critical point on this cup down shape, then that must be a max. If I have a critical point on a concave up, right, or cup up shape graph, then that critical point has to be a min. So that's kind of the idea behind the second derivative test. Remember back here we said that when the function was concave up, that means that the first derivative is increasing, which means the second derivative is positive. So for our second derivative test, after we find the critical points and compute the second derivative, we test those critical numbers. And if the second derivative is positive, that means that the function is concave up, so we'll have a relative min. If when we test our critical number in the second derivative, we get a negative, that means that the function is concave down there, and the critical point will be a max. If we test the second derivative and we get 0 exactly, then we can't conclude if it's a max or a min. Likewise, if the second derivative is undefined, then that's not helpful either. We can't make a conclusion based on this test. So let's look at the same example that we just did using the first derivative test. Let's repeat that now with the second derivative test. So I'm going to start by finding the first derivative. I need to use the first derivative to find the critical points. So let's first figure out where f prime is equal to 0. So 6x squared minus 6x minus 12 equals 0. And again, I'm going to factor this. I'm going to factor this a little bit more quickly because we already did this problem. So I get x equals 2 and x equals negative 1. And there's no number where f prime is undefined. So now let's find the second derivative. So I'm going to take the derivative of the first derivative, and we get 12x minus 6. And what we do is we just test the critical points. There's no drawing a number line or anything like that. Okay, so f double prime of 2 is 12 times 2 minus 6, which is 24 minus 6, or 18. And 18 is positive. That means that the function is concave up, which means that at x equals 2, we have a relative minimum. Okay, when we test negative 1 into the second derivative, we get 12 times negative 1 minus 6, which is negative 18, which is a negative value, so I know the function is concave down there, and that means that if I get a critical point, it's going to be a max. So f has a relative max at x equals negative 1. Okay, so there's some advantages and disadvantages to this. The second derivative test is a little bit faster. If the derivatives are easy to compute, I have less stuff that I'm plugging into. But the second derivative test also gives me less information. It doesn't tell me where the function is increasing or decreasing. So if I'm doing a problem where I need to know where f is increasing and decreasing, then the first derivative test is the obvious choice. So for example, a graphing problem, I would want to use the first derivative test. If I have a function where it might be difficult to plug in, or I'm not interested in where f is increasing or decreasing, then I might choose the second derivative test instead. Okay, let's talk about concavity and inflection. So to begin with, let's look at some pieces of graphs here. On this first graph, I can see that my function f is increasing, and also f prime is increasing. These slopes of the tangent lines are going up. That means that my function is concave up. So here I have an example of a graph that is concave up and increasing. On this next one, I can see that the tangent lines are getting smaller as I move from left to right. So the function itself is still going up. So here also f is increasing. But because the tangent lines are getting smaller and smaller, that means that f prime is decreasing, so the function is concave down. On this third example, part C here, the function is moving down, so I see that f is decreasing. And the tangent lines are getting less negative as I move from left to right. So that means that f prime is increasing, so the function is concave up. So on the left, I can see the two examples that are concave up. If I look at the last example here, the tangent lines are getting more and more negative. They're decreasing, so f is concave down. But the function itself is also moving down. So here, f is concave down and also decreasing. So on the right, we have the two examples where the function is concave down. On the top, we have the two examples where f is increasing. And on the bottom, we have the two examples where f is decreasing. So increasing, decreasing is separate from concave up and down. Remember that the increasing, decreasing is when the derivative is either positive or negative. Concave up and down is when the second derivative is positive and negative. And those two are independent of each other. The way that we test for concavity is by looking at the second derivative. So here's our test for concavity. Now, there's not a first and second derivative test for concavity. We just have this one test, and we don't really have a name for it other than just the test for concavity. So first we're going to find the x values where the second derivative is either 0 or undefined. This is like a critical point, except it's for the second derivative. And for the first derivative, we use that convenient name, critical point or critical number, to tell us where the first derivative is 0 or undefined. And for no good reason that I'm aware of, there isn't a name for the corresponding numbers in the second derivative. We don't have a way to refer to the critical numbers for the second derivative. We just say this is where the second derivative is 0 or undefined. It's very cumbersome, but that's what we're stuck with. So what we're going to do is we're going to find those 0 and undefined values for the second derivative. We're going to draw a number line labeling those values, just like we did in the first derivative test. And then we're going to test numbers from each interval into the second derivative. So this test for concavity is very much like the first derivative test, except that we use the second derivative. However, this is not the second derivative test. So let's look at an example really quickly. Suppose my function f of x, we'll pick the same function that we had back here. 2x cubed minus 3x squared minus 12x plus 4. Okay, so I need to find the first derivative only so I can find the second derivative. So my second derivative is 12x minus 6. So let's figure out where f double prime is equal to 0. We get 12x minus 6 equals 0. So x equals 1/2. And there's nowhere where it's undefined. So we make a number line, and we put in 1/2. And then I'm going to test a number from each of these two intervals into the second derivative. So to the left of 1/2, I can pick 0. When I put in 0, I get negative 6, which is negative. So the graph is going to be concave down. If I put something to the right of 1/2 in, say 1, I'm going to get positive 6. Because that's positive, the graph will be concave up. So this is how we can check concavity. So let's put these two together and look at an example. So here f of x is x cubed minus 3x squared minus 9x minus 1. And what we want to do is find all of the relative extrema, y-intercept, where the graph is increasing, decreasing, where it's concave up or down. And now after we find all that information, we're going to use it to help us sketch a graph of the function. One of the easiest things to do is going to be to find the y-intercept. Maybe I'll begin with that. That's just the y value when x is 0. So f of 0 is 0 minus 0 minus 0 minus 1. So I have the point 0, negative 1. Okay, now let's look at where the graph is increasing and decreasing. And this will also help us find the relative maxes and mins. So I need to find the derivative, f prime of x. And then we need to figure out where the derivative is either 0 or undefined, right, the critical numbers. So f prime will be 0 when 3x squared minus 6x minus 9 is equal to 0. I'm going to factor out a 3. I'm going to factor again into x minus 3 times x minus 1. So when x minus 3 is 0, x is 3. When x plus 1 is 0, x is negative 1. There is nowhere where this is undefined because it's a polynomial. So now I'm going to make a number line, and I'm going to put the 3 and the negative 1 on my number line. And I'm going to test points from each of these 3 intervals into the first derivative. So let's try f prime of something to the left of negative 1. Let's say negative 2. So when I plug in negative 2, I get 3 times negative 5 times negative 1. And I'm really only interested in if it's positive or negative, and the 2 negatives make a positive. So I have a positive number. That means that the function is increasing. Between negative 1 and 3, a convenient number to plug in is 0. I get negative 9, which is negative, so the function is decreasing here. To the right of 3, I can plug in anything I like. I'm going to go ahead and plug in 10. So I have 300 minus 60 minus 9, which is definitely a positive number. So the function is increasing on that last interval also. That tells me that I have a relative max at x equals 1 and a relative min at x equals 3. So we found the relative extrema, we found where the graph is increasing and decreasing, we have the y-intercept. Now we can move on to concavity. For concavity, we're going to look at the second derivative. So I need to find f double prime of x. So that's 6x minus 6, right, using the power rule. Let's figure out where the second derivative is 0 and where the second derivative is undefined. It's a polynomial, so there's no solution. So I just have this one value, x equals 1. Now here's what I'm going to do. I'm going to put this 1, instead of making a new number line, a second number line for concavity, I'm going to put this x equals 1 onto the same number line that I used for my first derivative test. So 1 will go somewhere over here. Now I need to readjust this because this decreasing is from negative 1 to 3. So I want to make sure that I indicate that from negative 1 to 3 on both of these intervals now, it's decreasing. And I've broken that up because I put this 1 in here. Now I need to test to the left and to the right of x equals 1. And what I want to do is I want to test a number into the second derivative. So to the left of 1, if I plug in 0, I get 0 minus 6, which is negative. That means the function is concave down. I can also test over here, further to the left. If I plug in negative 2, we get negative 18, which is also negative, so the function is concave down. To the right of 1, I could plug in, say, positive 2. I'm plugging into the second derivative, so I have 6 times 2 minus 6, which gives me 6, which is positive. Positive number means that the function is concave up. And finally, I'm going to plug in something bigger than 3. We'll try f double prime of 4. So I have 6 times 4 minus 6, which is 18, which is positive. Now, some of you might have observed that if I did the second derivative test, I would not have needed to test 4 different things, because I only have to the left and right of 1. And that's true. What I was doing was just being careful. I was saying, oh, it looks like I have 4 intervals. I will check all 4. That's not necessary. It's just being careful. All right, the reason that I put all of this together on one number line is because that makes it much easier for the very last step, graphing. I do want to make a quick note. When we talked about concavity, when the function changes concavity, that's when we have an inflection point. So here we went from concave down to concave up at x equals 1. So it's worth noting that f has an inflection point at x equals 1. And we'll make a note of what this looks like on the graph. All right, so let's go ahead and try to graph this. The way that I'm going to begin this is by taking the number line that we just created a minute ago, and I'm going to redraw it underneath my coordinate axes for graphing with the corresponding x values. So right here would be like an x equals 0. I really only need -1, 1, and 3 though. So here's -1 on my graph. So -1. There's 1 on my graph. There's 3 on my graph, so there's 3 on my number line. So it corresponds vertically. And then I'm going to fill in the information that we had about increasing, decreasing, and concavity. So on this first interval, it was increasing and concave down. Then it was decreasing and concave down. Then it was decreasing and concave up. Then it was increasing and concave up. The other piece of information that we want to grab from this page is that we have this y-intercept at 0, -1. So when I draw my graph, I have a starting point on the graph here at 0, -1. Okay, what I like to do when I'm drawing my graph is to look at this information we have about concavity and increasing and decreasing and use it to draw a piece. So remember back here, we had these pieces of the graph, right? So here this was increasing and concave up, and I had this piece, right? Or I could think of concave up and just take the increasing side of it. So here I start with concave down, and I want the increasing side, so this shape. Here I have concave down, and I want the decreasing side, so this shape. Then I have concave up, and I want the decreasing side, so this shape. Then I have concave up, and I want the increasing side, so this shape. So I need to fit these together. Remember that we have a relative max at -1 and a min at 3. So since I have a max at -1, it's going to be higher than values nearby, so it's going to come down. And I want to have this shape here. So there's my bent down decreasing shape that I've drawn. Now, we don't really have information. I didn't plug in to see, is this point up here? Is it down here? Is it way up here? So when we're sketching a graph, we're missing a little bit of accuracy, and that's okay. What we're really just trying to do is fit together the information that we have. So the next piece is the shape that's bent downward and decreasing from 1 to 3. Okay. And then from 3 onward, it's bent upward and increasing. Moving back to the other side, to the left of -1, we have this bent upward and increasing. So there's the graph that we want to look at. Now, we can double check this by graphing on our calculator. And I should have the same shape, but it might be off by a little bit. It might not be perfect because we didn't check all of these points. We don't know where that negative, or where that 3, how far negative does that go? At -1, where is that y value? So what I'm going to do is to check it, but take it a little bit with a grain of salt, right? So remember the function that we were testing, or sorry, that we were graphing, was x cubed minus 3x squared minus 9x minus 1. And let's just see how we did. Okay, so some of this is off of my screen a little bit, so I'm just I'll zoom out. And you can see, yeah, this is kind of the shape that we have. Comes up, down, and back up again. And it looks like we were pretty close. I didn't label my y scale very much. So maybe, labeled appropriately, this would be very accurate. Okay, our goal here is not to have super accurate graphs by hand. What we're really trying to do is just look at how a function and its first derivative and its second derivative all relate to one another, and we're using graphs as a tool for doing that. All right, so let's look at another example that's not a polynomial. So here my function f of x is cosine x minus x, and we're going to look on the restricted domain negative 10 to 10. That's good because if we want to find all the relative extrema, trig functions might have infinitely many maxes and mins. Now this isn't exactly a trig function because we have this minus x in here, so it's a little bit more complicated than that, but the restricted domain will still be helpful. So let's look at what we want to find. We want to find the relative extrema, the y-intercept, the points where it's increasing and decreasing, where it's concave up and down, and sketch a graph. So all of the same information as last time. I'm going to start with the y-intercept. So we plug 0 into the function. Cosine of 0 minus 0 is 1 minus 0 or 1. So I have the point 0, 1. Plugged in 0 for x and I got 1 for y. Now let's look at the first derivative, f prime of x. The derivative of cosine x is negative sine x. The derivative of x is 1, so we have negative sine x minus 1. So now let's look for the critical point. So we're going to look for where f prime is equal to 0, or where f prime is undefined. So negative sine x minus 1 equals 0. So negative sine x equals 1. So sine x equals negative 1. So then to solve this, remember solving trig equations, we have to use an inverse function. I'm going to take inverse sine of both sides. So on the left, that will wipe out the trig function, and I'll just have x. And on the right, the inverse sine of negative 1. You're free to use your calculator, but make sure that you're in radians. So I'll show you how to do this on your calculator really quickly if you don't remember your unit circle. So we take inverse sine of negative 1. Oh, my calculator's in degrees. I get negative 90 degrees. If you're in radians like you're supposed to be, you might get some crazy number, but remember that typically my angles that I get when I'm in radians are going to be some fraction of pi. So if you just divide out pi, you can see, oh, it's a negative half of pi, or negative pi over 2. Okay, or you can just remember what your unit circle looks like. Remember that this gives me one solution. When I'm solving a trig equation, I get infinitely many. So I could have any multiple of 2 pi, or x could be pi minus this answer. And pi is like 2 pi over 2 minus a negative is plus pi over 2. So that would be 3 pi over 2 plus 2k pi. Now we're looking in the restricted domain negative 10 to 10. So what I want to do is list out all of the values that are actually between negative 10 and 10. So we're going to list our critical points. So when k is 0, I'll get a negative pi over 2. Out of the second one, I'll get 3 pi over 2. When k is 1, I'm going to have a negative pi over 2 plus 2 pi, which is negative pi over 2 plus 4 pi over 2, or 3 pi over 2. I say, oh, that's a repeat with what I have down here. So then I add another 2 pi to it, which is another 4 pi over 2. So we'll get 7 pi over 2. Okay, if I add another 2 pi, that's another 4 pi over 2, or 11 pi over 2. And at some point, I'll have gone beyond 10. So what I want to do is just, maybe I can use my calculator to help me and say, all right, what is 3 pi over 2? That's not more than 10. Okay, now what is 7 pi over 2? That is more than 10. So the 7 pi over 2 and the 11 pi over 2 are too big. We don't need them. Okay, but k can also be a negative number. So when k is negative 1, I subtract 2 pi. So it's subtracting 4 pi over 2. So negative pi over 2 minus 4 pi over 2 is going to give me a negative 5 pi over 2. That is between negative 10 and 10. The next one over, right, when I go down by 2 pi, negative 9 pi over 2, that's too far, so we throw that one out and we don't keep going. Okay, so we have 3 critical numbers from our first derivative. So I'm going to make a number line, and I'm going to put a hard stop here, -10 and 10, and I don't have anything to the left and to the right of that. In between, I have 3 critical numbers, -5π/2, -π/2, and 3π/2. Now, oh, sorry, whereas f undefined, there's no solution there. Sine x is defined everywhere. Okay, now just like before, I want to test each of my intervals. I don't have to test to the left of -10 and to the right of 10 because that's outside the domain of this function. So let's look at f prime, and I'm going to put in something to the left of -5π/2. I think that maybe -6π/2 or -3π would be easy to plug in. When I put -3π into my sine function, remember it's sometimes helpful to think about a unit circle. So I go -1, -2, -3π. That's over here. The y value is 0. So sine of -3π is 0. So I have -1. Because that's negative, it's going to be decreasing in this piece. And between -π/2 and -5π/2 is -2π/2, which is -π. When I put -π in, I get 0. So this is decreasing here as well. When I put in something between -π/2 and 3π/2, I can just put in 0. Sine of 0 is 0. So it's decreasing here. And finally, something bigger than 3π/2 would be like 4π/2, which is just 2π. When I put in sine of 2π, I get 0. It was negative, so it's decreasing here also. Okay, so the increasing, decreasing doesn't have to alternate. In this case, it's decreasing on every single one of my intervals. That means that we have no relative maxes, no relative mins. Okay, now let's look at the second derivative. When I differentiate negative sine of x, I'll get negative cosine x. When I differentiate -1, I get 0. So we just have negative cosine of x. Let's figure out where that's equal to 0. So we have cosine x is 0. So that means that x is inverse cosine of 0 plus k pi, 2k pi. When we take inverse cosine of 0, if I look at my unit circle, I'm looking at where I have an x value of 0. And that's going to be at an angle of π/2. So I get π/2 plus 2k pi, or negative π/2 plus 2k pi. Right, remember from our trig review. So if I want to make a list of the x values that I would get here, we'd have π/2. If I add 2π to that, 2π is 4π/2 plus π/2 is 5π/2. Okay, if I add another 2π, I'll have 9π/2. And I think that earlier we said, oh, 7π/2 was too big, so certainly 9π/2 is too big. If I subtract 2π, right, if k is -1, then π/2 minus 2π is π/2 minus 4π/2, which is -3π/2. Okay, subtract, when k is 2, subtract 4π, which is 8π/2, so π/2 minus 8π/2 is -7π/2. And that one, I think, is going to be too big. So that's beyond our domain. Okay, so there I just checked all of the π/2's adding and subtracting multiples of 2π. Now we're going to look at negative π/2 and multiples of 2π. So we could have negative π/2. When I add 2 pi, I'll get 3 pi over 2, which is fine. When I add another one, I get 7 pi over 2, which I know is no good. When I subtract 2 pi, I'll get negative 5 pi over 2, which is fine. When I subtract again, I get negative 9 pi over 2, which is no good. So I have some repeats here. When we go to label these on our number line, I'm going to try to go in order. We have negative 5 pi over 2, which is already on there. We have negative 3 pi over 2, which I need to add in. We have negative pi over 2, which is already on here. We have positive pi over 2, which I need to add in. We have 3 pi over 2, which is already in here, and then we have 5 pi over 2, which we need to add in. When I add in values, in this case it doesn't really matter because it's always decreasing, but as a matter of good habit, when I break up one of these intervals in half, it's a good idea to just split up and say that's decreasing on both sides. So I split this interval in half. It's now 2 decreasing intervals, and again this last interval was split in half, so I break that up into 2 decreasing intervals. Now what I need to do is I need to test a bunch of points into my second derivative. So we're going to need a little more space for that. So I'm going to look at f double prime, and something to the left of negative 5 pi over 2 is negative 6 pi over 2, which is negative 3 pi. So I just want the opposite of cosine of negative 3 pi. When I put negative 3 pi into the cosine function, I get negative 1. With another negative on it, gives me a positive 1. So this is going to be concave up. When I move to the next one, between negative 3 pi over 2 and negative 5 pi over 2 is negative 4 pi over 2, which is negative 2 pi. And cosine of negative 2 pi is 1. With an extra negative on it, gives me a negative 1. So we proceed on down the list. Between negative 3 pi over 2 and negative pi over 2 is negative 2 pi over 2, which is negative pi. Cosine of negative pi is negative 1. So I have the opposite of negative 1, which is a positive 1. So it's concave up. Between negative pi over 2 and positive pi over 2, I can plug in 0. Negative cosine of 0. Cosine of 0 is 1. So with that negative on the outside, I have a negative 1, so it's concave down. Okay, and I'm starting to see a pattern here, right? I want to check pi and then 2 pi. When I plug pi into cosine, I get negative 1. The opposite of negative 1 is positive 1. Between 3 pi over 2 and 5 pi over 2 is 4 pi over 2, which is 2 pi. So the opposite of cosine of 2 pi is the opposite of positive 1, which is negative 1. So the function is concave down. And then finally, bigger than 5 pi over 2 would be 6 pi over 2, or 3 pi. So I have the opposite of cosine of 3 pi. Cosine of 3 pi is negative 1. The opposite of negative 1 is positive 1. So the function is concave up. Okay. That's a lot of detail. Now, let's put this all together and sketch a graph. Once again, I'm going to put my axes in, and directly underneath, I'm going to recopy that number line that we just had. Our domain is negative 10 to 10, so I don't have anything outside of that. Okay. And then we want to go negative 5, negative 3, negative 1, 1, 3, 5. Pi over 2's. So at negative 5 pi over, well, let's fill this all in. It alternated with the concavity, and it's always decreasing. So up, down, concave down. Always decreasing. Going back up, we had a y-intercept of 0, 1. So when x is 0, y is 1. So moving to the right, this is in the middle of an interval that is concave down and decreasing. so we want to have that bent down shape. Then it's still decreasing, but now it's bent up, and then bent down, and then bent up. Going the other way, we have this bent up and decreasing shape. And we have a bent down and decreasing shape, and then a bent up and decreasing shape. And there's our graph of y equals cosine x minus x. Did the question ask us for inflection points? I did not, but we have a bunch, right? So every one of these values in the second derivative ended up being an inflection point because concavity changed. Okay, so it did not ask us to write this down, but maybe just as an extra, we could say that f has no relative max or mins. F has inflection points at x equals negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, pi over 2, 3 pi over 2, and 5 pi over 2. Okay, that's it.